In this video, I'm going to show you 25 A-level physics equations derivations. It's quite a mouthful. This isn't all 25 equations. I'd love to tell you this is all 25 equations you need to learn the derivations for. That's not quite the way it is because different A-level courses have different requirements. So certain derivations, like number 1, 2, 3, 4, 5, and so on, you can expect those to be on your A-level, or at least you should know them. Others, for example, Thomson's E over M measurement or Millikan experiment, Fizzo's experiment, that's because of the option that we do in my school, which is the turning points option. If you do, let's say, engineering as an option, then you would have to know things like moment of inertia, angular momentum, that sort of thing, but we haven't got that in here. It's just these 25. So some of these will be useful. If you're doing turning points for AQA, they will all be useful. This is the AQA turning points list. So let's get started with number 1, diffraction gratings. So I start by drawing a diffraction grating, just simply as an array of slits, and I look at two adjacent slits, and I consider two paths, the 0th order path for rays of light, and then the nth order. And for the nth order, every point along these rays, we still have the rays in phase with each other, which means that they must still be in phase along this blue line here, which means that this extra bit, this path difference, has to be an integer multiple of lambda. So for the first order, that is 1 lambda path difference. For the second order, it is 2 lambda. For the third order, it is 3 lambda. So I've labeled this n lambda for the nth order. This angle here between the nth order and the 0th order must be the same as this angle here because the ray is 90 degrees to this line that represents where the rays are in phase. And the red ones, the 0th order, is 90 degrees to the diffraction grating. So we've just rotated the whole lot around and by an angle theta. So theta there is the same as theta there. And this is a right angle between the blue lines down here, which means we can use sine of theta equals the opposite, that's n lambda, divided by the hypotenuse, which is d. Rearrange it and you get that equation there. Now, Young's double slit's a little bit more involved. So with Young's double slit, we have to make what's called an approximation, the small angle approximation. And I've labelled the slits A and B. The distance between the slits is S. And the centre, right between the two slits, I've called this O. Now, because we've only got light coming from these two slits, not an infinite array of slits for what we've got with a diffraction grating, what we actually want to look at is where the light is incident upon a screen. So on this screen, I've called point C the point that is directly opposite from O, so the line connecting CO is perpendicular to the slits, but also perpendicular to the screen. Point D up here is the first bright fringe away from that centre C. And I've exaggerated it on this diagram. And D is the distance between the slits and the screen. We use a big D now so we don't get it confused with the D from the previous equation. Similarly, we use an S for the distance between two slits rather than a D, which we had for the previous equation, just to make sure the equations are kept separate and we can understand what's going on. Now, the two red rays have the same length, so the path difference between them is 0. But the two blue rays, the one at the bottom, that's BD, is longer than the one at the top, that's AD. And BD is longer by distance BE. And that distance is lambda, that's the path difference, if we have the first bright fringe away from the centre. So we now have two triangles, if we draw this diagram out. We've got the triangle ODC, or what do I call it here, COD. That's fine, and the angle theta here can be calculated by the arctan of W over D, no problem. But what's going on with a little triangle? Well, this purple line here, which connects A to E, that line connects the 2 points where the phase difference is 0. These 2 points of the blue rays are at the same phase. That's fine. That has to cross the orange line OD at 90 degrees. The angle at E and the angle at A are very, very small. Very close to 90, very small difference from 90 degrees. And the greater D is, or I should say the larger d is compared to s, the closer to 90 degrees the angle at E and the angle at A become. They can't be 90 degrees because if they were, the rays would not converge. But given that the slits are so close together, it's a pretty good approximation that we can say the angle at E is 90 degrees. It will get closer and closer to 90 degrees as D gets bigger and bigger. So now we've got a right-angled triangle. This little triangle here, EAB, is a little right-angled triangle. And the angle theta here will be the same as the angle theta here. Not quite. It'll be nearly the same. And the bigger D becomes, the closer this angle will become to this angle. They're going to be very, very small angles. They're going to have to be very small angles. So with this little triangle, approximately a right-angled triangle, we can say that the sine of theta is equal to the opposite, that's lambda, divided by the hypotenuse, that's s. So we've got these two expressions here. Now the thing about small angles is that the function for sine theta and the function for tan theta both cross the origin 0. And actually, around this region, the two functions look the same. They're almost the same. The smaller the angle becomes, the closer sine theta gets to being equal to tan theta, or if we're using radians, to theta. So, again, small angle approximation for small thetas, sine theta equals tan theta, and that will happen when d is very much bigger than s. So if sine theta equals tan theta, then sine theta, which is lambda over s, is equal to tan theta, which is w over d, and you can rearrange this however you like. I have got detailed derivations of those previous two in separate videos on my YouTube channel. So what about potential dividers? Well, here I've got a simple circuit. And in this simple circuit, I've got a potential difference across the power supply, which I'm calling V0, a potential difference across this top resistor, which I'm calling V1, and a potential difference across this bottom resistor, which I'm calling V2. Now, the current passing through the power supply, I'll call I0. The current passing through the first resistor, I'll call I1. The current passing through the second resistor, I'll call I2. And we can use our definition of resistance. So R1, the resistance of resistor 1, is V1 over I1. R2, the resistance of R2, of resistor 2 down here, is V2 over I2. And from the power supply, we can say that the total resistance between this point up here and this point down here, that is going to be V0 divided by I0. So we've laid out all our terms. Now, Kirchhoff's first law, I think I spelt this right. It's a transliteration anyway, so it doesn't matter. Anyway, Kirchhoff's first law is that the current flowing into a junction equals the current flowing out of a junction. Well, there are no junctions, so pick any point on this circuit. The current flowing into that point will be equal to the current flowing out of that point, which means all these currents are equivalent. Now we can write down, let's just do it in terms of resistor 2. Let's imagine we want to know the potential difference across resistor 2. We can write down that the current through resistor 0, or should I say the current through the power supply, is V0 over RT. So that's just rearranging this equation here. The current through resistor 2 is V2 over R2, but that is also I0 because of Kirchhoff's first law. Well, if this top expression equals I0 and this bottom expression equals I0, then the top expression equals the bottom expression. And now we could just rearrange that to make V2 the subject. You could do exactly the same thing for the top resistor, for resistor 1, and you get this expression. That is to say that the potential difference across the bottom resistor is equal to the total potential difference across both multiplied by its share of resistance, and the same for the first resistor. Moving on to momentum, pretty standard derivation you should know. So momentum, lowercase p equals m times v. And if we want to know what that is in terms of kinetic energy, the way we could do that is we can square the momentum equation, and the kinetic energy equation is E equals half mv squared. It's nearly right. We just need to multiply both sides by m to get half m squared v squared. Well, m squared v squared is p squared, so me equals half p squared. We can multiply through by 2 to get 2me equals p squared, and take the square root of both sides to get the momentum equals the square root of 2m multiplied by the kinetic energy. There it is. All the way through this video, I've put a yellow square around, or yellow rectangle, around the derived equations. So wavelength of electrons from an electron gun. We've got this equation for momentum in terms of kinetic energy from the previous derivation. Now, the work done on an electron moving across a potential difference V in an electron gun, which is what this diagram is trying to represent, that work done is equal to the kinetic energy gained by the electrons moving across that gap. So here is our anode, and over here is our cathode, and we've got power supplies connected to this that I haven't shown on this diagram. What I have shown is that V, the potential difference between them. Sometimes we use a subscript A to indicate that it is the anode potential difference. Okay, so we've got our equation, P equals the square root of 2me. If we just substitute for E, the lowercase ev, we end up with this expression. And remember in de Broglie's hypothesis, de Broglie wavelength, lambda is h over p. So we can substitute this in for p, and we end up with this expression. No problemo. Equation number 6, speed of electrons from the electron gun. Well, I've got this expression already, the energy that is gained by electrons moving across the gap. And as I said, that is equal to the kinetic energy the electrons gain. So I can say EV, that's capital V, is equal to half mv squared. That's a lowercase v. Do make sure your uppercase and lowercase v's are obviously different. Now I can multiply through by 2 to get this expression here. I can divide through by mass to get this expression here. And then finally I can take the square root of both sides to get V is equal to 2E anode potential difference divided by m, all under the square root. Now equation number 7 is the radius of the path of a charged particle if it's in an magnetic field, So the force on a charged particle moving through a magnetic field is F equals BQV. At least that's the way we're writing it here. The magnitude of force, perhaps I should say, is equal to BQV. Well, that is going to be causing circular motion because the force will always be perpendicular to the velocity of a charged particle. That's Fleming's left-hand rule. So the equation for centripetal force, the force causing circular motion, is mv squared over r. If BQV equals F and mv squared over r equals F, then BQV equals mv squared over r. Now we can cancel one of the v's from both sides and make r the subject, and we get the equation we can see at the bottom there. R equals mv over bq. Equation number 8. The period, that's the time period, of a path of a charged particle in a magnetic field. The charged particle is moving in a circle. What is the time period of that circular motion? Well, the previous equation we derived was the radius of the path of the charged particle in the magnetic field. We're going to use that, but remember that we're moving in a circle, so the speed of the particle, not velocity, the speed, is going to be the distance travelled divided by the time. And if we're moving in a circle, the distance travelled is the circumference of the circle, 2 pi r, where r is the radius of the circle. And capital T is the time period. That's how long it takes for the particle to move around in a circle. So we could take this equation and we could substitute it into this equation if we wanted to. Actually, that's not quite what I've done here. What have I done here? I've substituted the other way around. I've taken this equation, mv over bq, and substituted it into that r there. And I ended up with v equals 2 pi over t, and instead of r, it's mv over bq. Now the v's will cancel, and okay, v divided by v is just the number 1. I've written it in this horrible way so you know it's not an I or an L or something. That's the number 1. I don't like writing ones like that, but I have done. Anyway, 1 is equal to 2 pi over the time period multiplied by mass over bq. It's interesting, q over m is the specific charge of the particle. So this is the reciprocal of the specific charge right there. If we make t the subject by multiplying through by t, we just get this equation here. The time period is inversely proportional to the specific charge. Moving on to equation number 9. We derived equation 7, the radius of the path of the particle in the magnetic field, and 6, the speed of a charged particle, an electron in this case, which has moved across a potential difference V in some sort of anode, some sort of cathode gun, some sort of electron gun. Well, in this case, we're going to make it more general. Rather than talk about the charge on the electron, we're going to replace that with Q, just the charge of a charged particle. So that's fine. What we could do is we could substitute this V into this equation. So equation 6 substitutes into equation 7 to replace that v. So equation 7 read r equals m over bq multiplied by v, but this is v instead, and it's q instead of e. Now, this is probably not the most sensible way of doing it, and someone's going to get all narked about the fact I've written these sorts of things like this, but it doesn't matter. It really doesn't matter. What I've got here is m divided by the square root of m. And m divided by the square root of m, well, m is just the square root of m squared, so that will cancel and give us the square root of m. Someone's going to say, you can't do that because plus or minus, it's fine. Okay, we're working with scalars, it's fine. And we can do the same thing with this. We've got square root of q over q, so we can get that to equal 1 over the square root of q. We can substitute those in to simplify things a bit, and we get this expression here. And then, look, let's just stick the b into the square root by making it b squared, and we end up with this expression here for the radius of the charged particle. And that's in terms of the potential difference we accelerated the charged particle across before it entered that magnetic field. Right, so that moves naturally on to velocity selectors. These are situations where the magnetic and electric force are both acting on charged particles, and only certain velocities of particles can move across a gap. So the electric force is Q, that's the charge of the particle, times E, that's the electric field strength. But the electric field strength, if we are in a uniform electric field, is V over D, where V is the potential difference. Maybe one of the metal plates that's causing an electric field is at zero potential, so V would just be the potential of the other one. Anyway, so we've got V, the potential difference between the two plates, and D is the distance between the two plates, producing this uniform electric field, which we can substitute into that equation to get the force, the electric force, electrostatic force on a charged particle, which is in a field produced by a uniform field produced by two metal plates with a potential difference V between them and a distance between them of D. So that is going to be equal to the magnetic force, BQV, for a charged particle moving through a uniform magnetic field as well. So if this equation equals F and this equation equals F, then that equation equals this equation. And you end up with this. The Q's cancel, and we make V the subject, and we get this. Now what you'll notice is that the potential difference divided by D was the electric field strength. So we could have actually left it in terms of electric field strength and had that the speed that the charged particles move through this velocity selector is determined by the ratio E over B, the electric field strength divided by the magnetic flux density. It could be either of these equations that you might be asked to derive. Moving on to equation 11, the induced EMF across the wire passing through a magnetic field. Well, remember Faraday-Lenz's law. You might not have seen it written quite like this, but this is what it is. This is the EMF equals minus the first derivative of the flux linkage. What is flux linkage? Well, it's the number of turns we have on a coil or something multiplied by the flux. And what is the flux? Well, that is the flux density multiplied by the cross-sectional area. So the flux linkage is NBA. And so our EMF is minus the first temporal derivative of NBA. Now for our simple case, N is 1. If we've got a simple wire passing through this magnetic field, that's what this diagram is indicating. Here's the wire at some time, and some time t later, the wire is over here, and this is a uniform magnetic field, and the wire's moving at a perpendicular velocity, v, perpendicular to the length of the wire, if you like, or displacement of charge moving across the wire. So we're going to say N equals 1. Fine. Well, let's remember that displacement of the wire from this position here to this position here, that displacement is equal to the velocity of the wire multiplied by the time it takes for the wire to travel across that gap, which means that we have this area here represented by the displacement of the wire as it moves from this position to this position multiplied by the length of the wire that's in the magnetic field. So S multiplied by L, or substituting for S, VT multiplied by L. If I divide through by time, I get the area divided by the time it takes for the wire to move from this position to this position. In other words, the rate that the area is swept. That's equal to VL. Now that's important because in the equation for Faraday-Lenz's law, I got that with the n equals 1, so minus 1b, and then dA by dt. And the reason why I've moved the b outside is because it's a uniform magnetic flux density. And I moved the n outside because it's a fixed number of turns, which in this case it's just one length of wire, so 1 has been taken outside. So dA by dt, if the speed is constant and everything is constant, then it's moving through and sweeping at a constant area rate, which means dA over dt is just A over t. And I've done that because that way I can substitute A over t with VL and get this equation. Now the minus is somewhat optional, okay? The minus is there because of Lenz's law, and you might be asked to derive this without the minus, or the minus might be in brackets. It doesn't really matter about the minus. That just gives you information about the polarity of the EMF on these wires. It's not too important, actually. You can work out the polarity by just considering induction at a later point. But there we go, BVL, and that's how you derive it. Moving topics, speed of a satellite. We have that the gravitational force, this is Newton's law of universal gravitation. I've used capital M, lowercase m to indicate two different mass bodies. The big M is the big mass body, maybe it's the planet Earth, and little m is the small mass body, maybe it's the satellite that is orbiting the Earth. But this would work just as well for a planet M lowercase m orbiting a star, capital M, or anything like that. You know, if you've got some sort of probe orbiting the moon, then big M is the mass of the moon, little m is the mass of the probe. So that's our Newton's law of universal gravitation. The gravitational force is going to cause circular motion, so that's mv squared over r, the centripetal force. And the little m in this equation for centripetal force is the same as the little m in this equation for Newton's law of universal gravitation. And if the top equation is equal to F and the bottom equation is equal to F, then the top equation is equal to the bottom equation. And now we can cancel. Divide through by mass, divide through by r, the radius of that circular motion. We end up with gm over r, which is equal to v squared. Take the square root of both sides. We have the speed of a satellite, which only depends on the mass of the body which is being orbited by the satellite, and r, the radial distance from the center of the body that's being orbited to the satellite. This is assuming circular motion. So if you have elliptical motion that is not circular, then you have to do something a little bit more extravagant. Let's move on to number 13. The time period of such a satellite. So from the previous equation, we've got the speed, and that's fine. We also know that we're travelling in a circle. So the speed is equal to the distance, which is the circumference of the circle, 2 pi r, divided by the time period, how long it takes for the satellite to move around in its orbit once. So if this is equal to v, and this is equal to v, then this is equal to this. Off we go. Square root of gm over r is equal to 2 pi r over capital T. Now I can square everything to get to this stage here, and at this stage I'm pretty much done. Well, I'll multiply through by r and multiply through by t squared, and I'm pretty much done. But it's not nice to have constants on the left-hand side and constants on the right-hand side. We usually like to look at proportionalities and relationships between variables, so we like all the constants bunged together. So that's what I've got here. I've got t squared is proportional to r cubed, or r cubed is proportional to t squared just by dividing through by the constant. Or I could take the square root of everything and get t is proportional to r to the power of 3/2. Or instead I could have taken the cube root of everything and had r is proportional to t to the 2/3. Any of those is fine. They're Kepler's third law. And what you're asked to show, well, pick one. I don't know what you'll be asked to do. Number 14, average kinetic energy of a particle in an ideal gas. Here's our ideal gas law. I'm using a lowercase p here for pressure at the moment. Should have been more consistent because later on I'm going to change that, but that's what I'm using at the moment. A lowercase p for pressure equals nkt. Fine. Now, equation 16, which we're going to derive later. I've done this in a peculiar order. Okay, we're going to do 16 later, but this is the equation you derive from 16 later on. If that's equal to PV and that's equal to PV, then that is equal to that. So I've written that down. NKT equals this futurely derived equation. The n's cancel on both sides, and we multiply through by 3 to get this equation here. Now, this equation, it's looking pretty close to kinetic energy on the right-hand side. We just need half m, and then this is an average c squared. So let's just divide everything by 2, and you get 3/2 kT is equal to that right-hand term there, which is the average kinetic energy. So the average kinetic energy is 3/2 kT. Gas density. There's a few ways you could be asked to define gas or to determine gas density. We know density is equal to the total mass of gas divided by the volume that mass of gas occupies. Now, the total mass of gas is equal to the number of particles of gas we have got multiplied by the mass of each of those particles, which means the number of particles we've got is the total mass of gas divided by the mass of each particle. Now, remember that ideal gas law? We can substitute n, the number of particles, into that equation to get this equation here. And then we can divide through by v and multiply through by m and divide through by k over t, basically rearrange this equation to get mt over v, which is here. Well, mt over v, we already said that right at the start, was the density of the gas. So there we are, we've got the density of the gas expressed in terms of the mass of a particle of gas, the pressure of that gas, the constant k, and t, the absolute temperature of the gas. But what if I don't know the mass of a particle of gas? What if I know the molar mass? Well, the molar mass, mR, is equal to the mass of a particle multiplied by Avogadro's number of particles. That is what molar mass is, the mass of a mole of particles. So m is therefore equal to the molar mass divided by Na, which can be substituted into the previous equation over here to give us this expression. And then you need to know, in terms of ideal gas laws, the relationship between K and R. Well, this is the relationship between K and R, and if you're not convinced of that, just take the two different formulations of ideal gas laws and rearrange them, and you'll find this must be true. So you take this equation and you substitute for Kna, and here you go. The density of the gas in terms of the molar mass of a gas and the other constants. Right. Now you see why I left equation 16 till later. It takes up a lot of space. The kinetic theory equation. Let's imagine we have a cube, a box cube with length of each side L. And at the moment I'm going to place a single gas particle in that box. The gas particle has a velocity with components in the 3 different cardinal dimensions. And I'm going to call each of those velocities a different letter. So the velocity in the x direction I'm going to call u, the velocity in the y direction I'm going to call v, and the velocity in the z direction I'm going to call w. Let's just look along the x direction for now. Along the x direction, the particle is going to be bouncing backwards and forwards between the 2 sides. And there's 2 ways of doing this. One way is to consider 6 faces, and the time it takes to travel from one side to the other is, let's call it t, and the distance that the particle travels is L. The other way of doing it is to consider 3 different directions, only focus on each side, on one side, the collision, and say that it takes t seconds to travel to L. In other words, from this surface away and back again. That's a distance of 2L travelled in a time t, giving us an average speed of u. You can actually do it either way. If you don't have that 2 there, you're going to end up having 6 different contributions to the pressure. If you do have this 2 here, because I'm considering there and back, I'm only going to have to worry about 3 contributions to the pressure. Well, 1 times 6 is the same as 2 times 3, so it doesn't really matter which you do, but this is the way I'm doing it. So t is the time between collisions with the shaded wall, just looking at that one wall, and I rearrange this equation to get 2L over u. The change of momentum of that particle, and I'm only looking at the component of the change of momentum in the x direction, is going to be the change in mass times u. Well, mass isn't changing, so mass times the change in u. The change in u is negative, it's minus, it's to the left, 2u. So the change in momentum is minus 2mu. Fine, no problem. Now the rate of change of momentum is the force. So a single particle on that wall is being pushed, I should say, by that wall to the left with a force equal to its rate of change of momentum. This is the change of momentum. I've got an equation for t, which I can substitute into here, 2L over where is it? 2L over U. So 2L over U substituted in here gives us 2L. The U goes up there, multiplied by that U to give us U squared. The 2's cancel, and we get this. Now, it's negative. And the reason why it's negative is because the force on the particle when it collides with that wall is to the left, which means, Newton's third law, the force on the wall is to the right. If the particle's being pushed left by the wall, then the wall is being pushed right by the particle. So we can neglect the minus sign when we're considering the force on the wall. Now, the contribution to pressure caused by that single particle, and only considering collisions with this particular wall, is going to be equal to the force of that particle striking that wall divided by the cross-section, the area of that wall. Well, the area is L squared, because I made sure of that. So that means that we are going to end up with the force, mu squared over L, notice there's no minus, because we're looking at the wall now, multiplied by, well, it's divided by A, so multiplied by 1 over A, which is L squared. So this becomes mu squared over L cubed. Now, that is the contribution to the pressure of a single particle, and that is a scalar. Pressure is a scalar. So if I consider all three directions, then there are pressure from one, plus pressure from another, plus pressure from another. So that's P plus P plus P, that's 3P. And the right-hand equations, add them all together, that's what I get. mu squared over L cubed plus, in the y direction, mv squared over L cubed plus, in the z direction, mw squared over L cubed. Now I can substitute out the m over L cubed, and I end up with this expression here, and L cubed, I know, is the velocity of the velocity, I saw a V, the volume of this cube. So there we go, L cubed is equal to V. And it says this 3P is per particle, so I can actually multiply every single thing by how many particles, the right-hand side, I should say, by how many particles. I don't have to do the left-hand side because that's the contribution on that face. I don't have to do anything to that. So 3P equals, it's now going to be m divided by v, because it's m divided by L cubed. So m divided by v multiplied by this term here, which is an average for all these particles multiplied by how many particles I've got. And then I can use Pythagoras on this, because I've got these three different directions, the x, y, and z direction, and I've got the sum of the squares of the velocities in those directions. Then the square of the velocity vector, not taking each component separately, is going to be c squared. So I end up with this expression here. Okay, what have I done here? I've multiplied through by v, I've divided through by 3, and I've replaced this average term here with the average velocity. There it is. A little thing about this average velocity, if I were to take the square root of that, I would have what's called the root mean squared. Okay, I've taken every velocity, I've squared it, I've calculated the mean of that, and then I square root it. That's the root mean squared. So this term in the triangular brackets is the root mean squared velocity squared. That's what that is. So you might have a derivation where CRMS squared appears in it. That is actually exactly the same thing as what's in this triangular bracket. Now we can actually go a step further to this. If I divide through by n to get this expression here, just like that, I've got PV over N, and I recognise that from the ideal gas law, PV equals NKT. Notice I've had to use capital P's for pressures here. I should have said this, because I used a lowercase p for momentum. So do be strict with yourself about that. So PV over N is equal to KT from the ideal gas laws, from one of the ideal gas law equations, the one for number of particles rather than the molar ideal gas law equation. So the molecular one instead. So anyway, we replace PV over N with KT. You get KT equals a third m, and then this root mean squared velocity squared. Well, that's fine. We can multiply through by 3 and get this equation here, and the left-hand side starts looking a bit like kinetic energy, or average kinetic energy, mc squared. Well, the average c squared, m root mean squared speed squared. So if I halve everything, then I've got kinetic energy on the left-hand side, which is just, I'm going to call it E, and I've got 3 halves kT on the right-hand side. And that's how you can derive E equals 3 halves kT. Now, moving on to what I think all students should know, but it's specifically talked about in the turning points option of AQA, Thomson's measurement of the specific charge of the electron. And this is the experiment where we have electrons following a circular path in a uniform magnetic field. So the uniform magnetic field on these particles. The particles we're talking about are electrons, so I'm using E for the charge. This is the force on an electron in a magnetic field with flux density B moving with a velocity V. And that force as a vector will be perpendicular to B and perpendicular to V. But we're just dealing with scalars. The particle's going to go in a circle because F is always going to be perpendicular to V. So circular motion, centripetal force, F equals mv squared over r. And if the top equation equals F and the bottom equation equals F, the top equation equals the bottom equation. There we go. We can cancel one of the V's and rearrange to make E over n the subject, and by dividing through by B and M, and you get this expression here. Might be useful later. Millikan's oil drop. The radius of an oil drop. There's lots of parts to Millikan's experiment. Millikan's experiment was where we measured the charge of oil drops and determined the granular nature of the charge of the of charges to work out that there was an electron charge. Measured the electron charge by the interval between the granular charges on an oil drop. So that's what we're doing here. This is a standard derivation that you need to know for the turning points option. The weight of an oil drop is the mass of an oil droplet times the gravitational field strength. And if the oil droplet is moving through a fluid, it's going to experience a drag force, I've used D for that, equal to 6 pi eta RV. That is Stokes' law, and it's only valid for spherical objects moving with radius r, moving relatively slowly through a viscous fluid. This is laminar flow around the spherical object. If you have any sort of turbulent source of air resistance, this equation doesn't work. The air resistance there is closer to v squared, or even equal to or proportional to v squared. But this is Stokes' law. Well, at terminal velocity, the weight of the oil droplet is equal to the drag, ignoring buoyancy, ignoring upthrust. So W equals D. So that means mg is equal to 6 pi eta RV. Fine. Well, the mass of the oil droplet is its density multiplied by its volume. So we can substitute that into the equation and get density, volume, gravitational field strength for the oil droplet equals 6 pi eta RV. Well, the volume of the oil droplet is spherical, so 4/3 pi r cubed. So we can substitute that in, and we get this expression here. And now we can cancel pi on both sides, cancel an r from both sides, multiply through by 3, and we get this expression here. Rearrange it to get r squared as the subject, and then divide through the right-hand side to get a simpler sort of fraction. Rather than 18 over 4, we've got 9 over 2, doesn't really matter. And then take the square root of both sides, and there we are. We know the viscosity of air, we know the terminal velocity of an oil. That was the school bell. Might edit that out later. If we know the viscosity of the air, that's eta, the terminal velocity of the oil droplet, that's v, the density of oil, that's rho, and the gravitational field strength on Earth, that's g, we can calculate the radius of the oil droplet, r. And of course you can measure viscosity of air easily enough in the lab. You can measure the density of oil easily enough in a lab. You can measure the gravitational field strength easily enough in a lab. You can use a microscope to measure, with a scale on it, to measure the terminal velocity of an oil droplet v. So that's all measurable. What about the charge on the oil droplet? Well, we're going to need to use that radius later. It's quite involved here. The weight of the oil droplet is still mg, and the force that the oil droplet will feel upwards if there's an electric field is equal to the charge of the oil droplet multiplied by the electric field strength. The electric field is provided by two metal plates with a potential difference across them, Vp. I've used the subscript P because I use V later on for volume as well, and we don't want to get the two V's mixed up. So the weight is going to be equal to the electrostatic force, W equals F. And we could write that in there. We could rearrange this to get mg over q equals E. We don't even need to do that. This is the electric field strength, the potential gradient. We can substitute that into the that's a better way of doing it. Substitute the potential gradient into the electric field strength to get mg equals q Vp over D. Rearrange that to get q as the subject, and there is our equation for the charge. You know, if we can measure G, the field strength in a lab, we can measure D, distance between the two metal plates, and Vp with the voltmeter, the potential difference across those metal plates, and that is the equation as often you are asked to derive it. My issue is that you can't measure the mass of the oil droplet, it's too small, but we can work it out if we know the oil droplet's radius and the density of the oil droplet. Mass equals density times volume. Volume is spherical, so there's the equation for a sphere. So mass is therefore equal to density multiplied by that volume. That's what that is. For number 18, we know what the radius was, so we can substitute that in and we get this. And then, you know, people cleverer at maths than me can probably spot immediately how to simplify this. I had to go through quite a few stages here. Reminded myself that rho is the square root of rho squared. For some reason, that allowed me to simplify the rho down here. And I can't remember what I did here. I made Q the subject because that's what I wanted was Q. Oh, no, this is the previous equation. There we are. Forgot what I did. This is the previous equation, but instead of M, I've put in the 4 pi cube root of, 4/3 pi over Q, the square root of rho, blah, 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 blah. So there it is there. That term is the mass in this equation. And now I just tidy things up. Again, I've got a silly thing here about G, so I can only get one G in the equation, otherwise I've got G appearing a couple of times. So there we are, I've only got one G, a nice simple G down there. Then I remind myself 4 is 2 times 2, and 2 is the square root of 2 squared. Honestly, I'm not that good at maths, so that's why I've used these silly little steps, which helps me simplify some of the numerical part of this. I mean, look at this. Simplifying some of the numerical parts. I mean, look. I couldn't spot that 9 to the 3/2 was 27. I had to work it out slowly, and 27 over 3 was 9. And you simplify and you simplify and you simplify again, and you end up with an equation like this. Now, this is a better equation, I think, because the charge can be determined from D, distance between plates, eta, viscosity of the air, not the oil, the air, V, terminal velocity, we can measure that through the microscope's view, Vp, the potential difference across the plates, rho, the density of the oil, you can measure that in the lab, and G, gravitational field strength, and so everything else is just numbers. I think that's quite a nice equation. Also in turning points, measuring the speed of light. So imagine we've got a gear here with teeth and gaps in it, and light passes through one of the gaps, reflects off the mirror and comes back. If the gear is not turning, it's going to come straight back through the same gap, but if the gear is turning fast enough, then that light is going to pass through a gap, reflect off the mirror, and then hit a tooth. And we'll see that the light becomes blocked. It will become dark. And you can use beam splitters and telescopes and all this sort of thing. But that's all we need. So the speed of light is going to be the distance it travels between the gear and the mirror. That's big D. Times 2, because it's there and back, divided by the time it takes to get there and back, which I'm calling lowercase t. And if the light is blocked, and this is an interesting one, then the time it takes is going to be the time period divided by twice the number of teeth. Now, why is it twice the number of teeth? Because there are n teeth, then there are n times 2 teeth and gaps. And you need the gear to rotate not one tooth circumference, one tooth distance around. You want it to rotate half of that around so that the light that passed through a gap hits a tooth on the way back. It's difficult to visualize, but that's what we're trying to do. So that's where the 2 comes from. So period of rotation of a gear, blah, 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 blah. That's what I've said there. So the time then, we can replace the time period with 1 over the frequency, and we end up with this expression, which we can substitute directly into the speed of light to get C equals 4dFn. F is the frequency of the gear rotating, D is the distance between the gear and the mirror, and N is the number of teeth. Now, you could have this equation in terms of angular frequency, where you replace 2 pi f with omega, so f equals omega over 2 pi, all that sort of thing, but that's fine. Now, relativistic speed in terms of energy. Energy of a body is equal to mc squared, according to Albert Einstein. And, unfortunately, our exam board insists on the idea of relativistic mass, as nonsense as it is, where gamma, the Lorentz factor, is given by this expression here. You're never going to be asked to derive that, but if you want to, you can do it with simple Pythagoras. So we substitute that in, we get this equation here. Well, you're actually given this equation, but it's for total energy. So if we want relativistic speed in terms of total energy, that's not too bad. It's just rearranging the equation we are given. So squaring the lot, e squared equals m naught squared c to the 4 over 1 minus v squared over c squared, then multiplying through by 1 minus v squared over c squared and dividing through by e squared gives you this expression, then subtracting v squared over c squared from both sides and, or I should say adding to both sides, and then subtracting m naught squared c to the 4 over e squared, and you get this expression here. Multiplying through by c squared, you get this, and we're just tidying it up. Take the square root of both sides, and you've got c squared under the square root, so you might as well take that outside. So that is E, the total energy of your particle, and you can calculate the speed, the relativistic speed, from that equation. What about kinetic energy? Well, again, we've the same steps here as previously, so we'll just jump straight in down here where we're given that equation. That is total energy, but the rest energy is m naught, the rest mass, otherwise known as the mass, c squared. So the total energy is the rest energy plus the kinetic energy. The kinetic energy is therefore the total energy, subtract the rest energy. The total energy was m naught c squared over the square root of 1 minus v squared over c squared. We're given that equation, it's up here. And then we just subtract the rest energy, m naught c squared, factor out the m naught c squared, you get this equation here, 23. There are lots of different ways that this can come up, finding the time for some sort of decay or attenuation, exponential decay or exponential attenuation. I'll just pick two here: potential difference across capacitor plates and number of particles in radioactive decay. But there are loads. You could talk about attenuation of amplitude for a lightly damped oscillator, or you could talk about temperatures converging in a system where two bodies are in thermal contact but start at different temperatures. There's all sorts of contexts where exponential decay or exponential attenuation is how you model what's going on. So they're both actually parallel side by side here. V equals V naught e to the minus t over RC. That's the equation for exponential decay of the potential difference across a capacitor when it is discharging. Or N equals N naught e to the minus lambda t is the equation for exponential decay of a radioactive source in terms of the number of radioactive particles that are left after a time t. So how do we work out what t is? We take the natural log of these equations. So natural log of the left-hand side equals natural log of the right-hand side. No problem. You can split this up, and then where you've got e to the minus t over rc, that's going to be minus t over rc, because natural log and e are inverse functions. That's what it says down here in blue. So then you've got this expression here. You can rearrange it to get t as the subject easily enough like that. And another way of writing the difference between two logs is the log of a ratio. And just one of the properties of logs is if you switch this ratio over, it becomes negative, because that's how reciprocals work. And so there we go. And this is the same one. I'm not going to go into that in any more detail. That's just doing basic maths. Right, last two equations then. Escape velocity. V here is the gravitational potential, which is equal to minus gm over r, where m is the mass of the body we're trying to escape from. And the potential is also defined as the work done per unit mass, and this is the mass that is trying to move across a potential difference v, and work done on it would be equal to w. Well, in this case, we are moving away from the Earth towards infinity, if it's escape velocity of the Earth, or whatever we're trying to escape from. So the work done is going to be minus the kinetic energy, or I should say the kinetic energy is going to be minus the work done, because we're moving away from the object. So we've now got this equation here. We've got W here, we can rewrite it like this. Okay, EK over M instead of W over M, and the minus disappears because of the minus here. So we've got that. EK is the kinetic energy. Substitute that in, and we get this expression. Cancel the masses of the body, and you get this expression. Terminal velocity, not terminal velocity, escape velocity does not depend on the mass of the body that's escaping. Square root of both sides, there we are, that's our equation. A similar but different approach is equation is what happens when alpha particles are approaching a nucleus, using that sort of thing to work out the diameter of a nucleus or approximate the diameter of a nucleus, that sort of thing. So the distance of closest approach. So the potential is now an electrostatic potential, 1 over 4 pi epsilon naught Q over R. And the definition of our electrostatic potential is going to be the work done divided by Q. That's the same as it is for a gravitational potential, but instead the constant is M, the mass of the body that's moving across that potential difference. This is an electric potential difference instead, but it's still the work done divided by the charge that's moving across that electric potential difference. Now, the big charge we're talking about here is the charge that the nucleus of the atom, that the alpha particle, is incident upon. And that's going to be equal to Z, that's the number of protons, or the atomic number, multiplied by E, the magnitude of the charge of the electron, the elementary charge unit. So I can replace the Q with ZE, and I end up with this equation here. Now, little q is the charge of an alpha particle. So again, that's 2 times the magnitude of the elementary charge unit, or the 2 times the magnitude of the charge on the electron. So that can be substituted in, and we get this equation. Now, r is going to give us the distance of closest approach, so we rearrange this equation to get r, just like this, and we've got 2 over 4, so let's just call that. Oh, it looks like I've made a mistake here. That should be a 2, shouldn't it? That should be a 2 under that cursor. Let me hide that discreetly. Pretend that's a 2 under my cursor. I was so excited about getting this finished, I made a mistake on the very last line. That should be a 2, 2 pi epsilon naught. So in this case, we've got moving towards a nucleus, so r is decreasing, whereas in the other case, moving away from the planet, so r is increasing. So that kind of explains why you end up with EK equals W and EK equals minus W, the difference between these two. That should be a 2 there. I'm really irritated at myself, but I'm not re-recording this because it's long enough as it is. Hopefully you found that useful, and I will stop there.